Hello, my name is Sergey Popov. I represent Kharkiv National University of Radioelectronics. Today I am presenting a paper titled A Modified Neurofuzzy Counterpropagation Network and its Fast Adaptive Learning by Sergey Popov, Irina Plis, Olga Chala, and Alexei Golovin. In recent years, artificial neural networks have been a topic of general popularity and has been gaining increased momentum, mainly due to successful applications of generative deep neural network models in natural language processing, image processing and generation, etc. These are huge models with billions of parameters, which require very large datasets and enormous computational resources for their learning. But there are a lot of other scenarios where intelligent data processing is needed, but the amounts of data are scarce, few computational resources are available, while processing rate requirements are high and sometimes real-time response is required. Such requirements pose a significant challenge and put substantial restrictions on the choice of ANN architectures and learning algorithms that may be used for this task. One of architectures of choice for such strict conditions is a counterpropagation neural network, CPN, introduced by Robert Hecht Nielsen. Its architecture is quite simple. On slide 2, a forward-only architecture is shown that implements the direct mapping from X to Y. The full counterpropagation architecture can implement both direct X to Y and reverse Y to X mappings simultaneously, hence the name counterpropagation. The first hidden layer is a coherence self-organizing map, designed to solve crisp clustering problems, that is dividing the dataset into H non-overlapping clusters in the self-learning mode. A self-organizing map implements the winner-takes-all approach, meaning that only one neuron, which is called the winner, is activated at a time. The output layer is formed by the so-called Grossberg outstars, which are essentially modifications of the standard linear element and implement the memory function. Let's take a closer look at the layers functioning. When a new input signal X arrives, it is compared to weights representing centers of all neurons in the coherent layer, and one closest neuron, the winner, is activated. That is, the output of the winner is set to 1 and all the rest is set to 0. The learning phase consists of adjustment of the winner's weights so that it is pulled in the direction of the input signal X. This is represented by formula 2. Please note that only one neuron is activated and adjusted at a time. In the output Grossberg layer, the winner's output activates the corresponding weights in the output neurons. Please note again, as there is only one winner, only one weight is used to calculate the output signal at a time. This is equivalent to activation of a single memory cell with a corresponding output value y hat. During the learning phase, this output value is adjusted towards the reference signal y. Thus, the whole network implements a lookup table functionality with crisp clustering of the inputs. This is inefficient in two ways. First, as there is only one winner, whose weights and only corresponding output layer weights are adjusted at a time, this is slow. Second, for the same reason, the output signal is a stepwise approximation without intermediate values. Hence, to increase accuracy, much more neurons in the coherent layer are required to increase the number of clusters and reduce their size. To overcome these drawbacks, we employed a fuzzy modification to CPN, where each observation may belong to several clusters simultaneously with corresponding membership degrees calculated as shown in Formula 5. This means that not a single but several, in general all neurons, are activated to a certain degree by each new input signal. It is the so-called winner-takes-more approach. The learning rule is changed accordingly to Formula 6. It should be noted that at each time step the weights of all neurons are adjusted in contrast to the original algorithm. Similar changes are introduced to the Grossberg layer as well. The activations vector U is replaced with the membership degrees vector mu, and the learning algorithm 3 is replaced by the optimal algorithm 8. In case of a noisy data stream, it can be beneficial to use a balanced modification of the learning algorithm 9. Here, coefficient gamma, which lays between 0 and 1, defines a balance between filtering and following properties of the procedure. To demonstrate advantages of the proposed modifications, we performed simulation with both traditional and modified neurofuzzy CPN. We used a simple setup with 2 inputs, 9 neurons in the coherent layer and 1 output. Inputs x1 and x2 are sampled from the uniform distribution over the interval from 0 to 1. The corresponding output y is calculated as a Euclidean distance between x1 and x2. The first 1000 observations form the training set, and another 1000 observations form the test set. Both networks operate in online mode, processing all end training observations sequentially and only once, updating their parameters after each step k. Also, after each step, the mean absolute error is calculated over the entire test set. That is, we monitor how the out-of-sample error changes during the online training process as shown on slide 7. It is clearly seen how error decreases during the training process for both networks, while the modified network demonstrates faster convergence and lower error. Slide 8 shows how the optimal and balanced learning algorithms behave during online training dependent on the value of parameter gamma. As expected, lower values of gamma result in a faster but rather unstable learning. Increasing gamma stabilizes convergence at the cost of some reduction in speed. It's up to a researcher to choose the value of gamma most suitable for the task at hand. Experimental results are conveniently summarized in a table. The following observations can be made. First, neurofuzzy CPN consistently outperforms CPN by achieving comparable or better error with fewer training iterations. The improved performance of neurofuzzy CPN results in a 24% increase in accuracy over classic CPN under the same conditions. Modifying gamma allows for precise control over learning dynamics, balancing between noisy and stable training process. Adjusting gamma to higher values enhances filtering properties without significantly compromising on learning speed. Experiments demonstrate that our modified network performs effectively and outperforms the standard CPN model. This result suggests that neurofuzzy counterpropagation networks hold significant potential in real-time data processing tasks, where both efficiency and accuracy are critical. The ability to adjust gamma parameter offers flexibility, enabling the network to adapt to varying levels of non-stationarity in input data streams. Thank you very much for your attention.